All right. So we have gone through and talked about static failure theories for ductile materials and that are most typically applied to ductile metals. And that's because there is a ductile region in the stress strain curve before ultimate failure is predicted, right? So that's for elastic materials that fail in a ductile fashion. Right, if this is our engineering stress strain curve, right, we'd have a yield stress, a ductile stable plastic region, an ultimate strength, and then an unstable region here at the top. Okay. If we talk about brittle materials, for example, ceramics generally, or some phases of steels, right, they don't have that same type of behavior. All right, if they fail in a brittle fashion, there is no yield and ductility, right? So we can't apply the same failure criterion that we did. Because for brittle materials, if we go back to that uniaxial tension test, oops. All right. And if we have a ductile material, it'll fail with that sort of cup and cone in the 45 degrees geometry, right? And that tells us about shear stresses. Well, in brittle fracture, we don't have that 45-degree angle. We may have a failure that's more straight across, right, that has some roughness to it. Something like this, and so we don't use the same failure theory. So let's look at one sort of base theory and then some modifications for brittle materials. So failure is generally ultimate fracture instead of yielding. And in addition to having that condition, these materials can be asymmetric. So if you think about concrete, for example, it's a very complex material, or maybe some homogeneous ceramic. If I put it in a tensile test, the normal stress I would get to fracture that thing is lower than if I put it in a compression test and do the same thing. Okay, so we are going to state failure like this. We're going to say that brittle failure occurs when the first principal stress, right, we can still calculate a stress state, we just can't apply the same failure criterion to it. So brittle failure occurs when the first principal stress is greater than or equal to the ultimate tensile stress in tension, or the ultimate stress in tension. Okay. Or, right, that the third principal stress is less than or equal to the ultimate strength, but this time in a compressive mode. Okay. So we actually have two now material properties that are constraining the failure instead of just a single one. And so if we have a plane, so in plane stress, right, we only have sigma 1, sigma 2, or let's call it, like, when they do these diagrams, they like to call it sigma A and sigma B. So we'll define sigma A like this. That would experience failure, or sigma B less than or equal to, that would be ultimate tension, stress, ultimate compression, and that's a B. We can draw our failure window here. So we'll have stress A and stress B, kind of like what I drew for sigma 1, sigma 2 before. And so before we had sort of I'm just going to draw the maximum shear stress theory on here in dashed lines just so you can recall it. So that's if shear stresses are the criterion we're going off of. If we have normal stresses, then we don't have any combination of stresses. In these failure criterion, it's not like sigma 1 minus sigma 2 or whatever. It's just the values themselves of those stresses. And I'm going to draw the compressive side larger than the tensile side. And then I'm just going to connect them up with this here. So it's just a big square. Right? Now where this would be the ultimate stress in tension, and this would be the ultimate stress in compression, and then the same thing along the B axis. Right? So if as long as we're inside the big box, then that's the safe zone. So in some ways, this is much simpler than having to combine shear stresses in order to come up with something. Okay. If we have a 3D stress state, instead of having some six-sided shape being extended along some axis, now we just extend this rectangle along another rectangle. And so we just get a rectangular prism in 3D where we have sigma 1, sigma 2, sigma 3, where all of those stresses individually have to be lower than whatever the tension or compression values are, and then they would be in a safe zone. Okay. So this is, you might think this is very oversimplified, right? And so in some sense, you would be correct. And so if we look at some experimental data, and I'm just going to draw it on here, not quantitative, but just qualitatively. The tension situations are they align pretty well. So if experimental data sort of falls like that, it's the green X's along the first quadrant line there. And then if we take and we start going negative, right, it sort of still follows down. Okay, so far so good. But at some point, there is a cutoff here like this, that the data kind of follows. And so it's not, it's still not called anything related to shear stress, but what it's called is a modified Moore criterion, right? So Moore did, expanded his work just from thinking about a circle for a 2D approximation of a stress state. He thought about these failure things in general as well. So the modified Moore criterion says that there's sort of a cutoff on this corner here, where you can't be close to both axes and their respective failure stresses, right? One in compression and one in tension. And so you would get the same thing along the top here, such that this is symmetric, like that. Okay. So let's say you had some modification. There is a famous textbook that talks about failure theory by somebody called Dowling. And what you can do is use basically a factor to calculate some combination of these normal stresses. And then you just look for whatever the maximum one is. So you can use effective stresses. And these are factors from the textbook by Dowling. Okay. So we want to be a little bit more exact. We can say that there are 3 factors we can calculate, and they are combinations of stresses. So the first one, we'll call it C1, is a factor of 1/2, and then the absolute value of a difference of sigma 1 and sigma 2, plus a sort of a failure stress ratio. So ultimate stress in compression plus ultimate stress in tension, divide by ultimate stress in compression. and then times the sum of those two stresses, like that, and then close it up. And we can write the same thing for the other two combinations. So this one is for sigma 1 and sigma 2, right? So we can write the other one, right, which would be for sigma 2 and sigma 3, and the same for sigma 1, sigma 3. Okay. And so these are these Dowling factors. And then you define an effective stress, right, as being whatever the maximum is between, in this set here. So all of these factors, or just the principal stresses themselves, sigma 1, sigma 2, sigma 3. And so the safety factor, or the actually we'll call it a failure criterion first, then we'll calculate the safety factor. So this failure criterion would be, you would expect brittle failure when, right, your effective stress, whatever the maximum is of all those values, equals the ultimate stress and tension. Then you would predict failure. And you can define a factor of safety as the ultimate stress and tension divided by this effective stress, whatever it is. And so you're basically, instead of only considering the values themselves, right, the ultimate strength and compression and tension in that box, now we can also have a combination that's kind of the quantitative way to modify that failure criterion. Okay. So for some materials, this will be more accurate. And at this point, it's very unsatisfying to say this, but the failure criterion that's most appropriately applied is from history and observations, right? So if you have a part that's made of zirconia, right, and you say, I want to know when this thing is going to fail. Maybe it's a large rolling element bearing, right? So it's got spherical balls of zirconia inside of metal raceways. And this is a common materials that are used for this. And you want to say, okay, if I can come up with a stress state inside of this zirconia, I want to know how much load I can apply through this bearing before the thing is going to fracture, right? Now, in that case, the steel might yield before the zirconia fractures. But if you knew the ultimate strength in compression and tension of zirconia, and you knew the stress state, then you could apply this failure criterion relatively easily, even with the modified Moore model. All right. So, yep, that's all it is. So it's pretty simple. Okay. So that's kind of the end of the static failure criterion, yield criterion, and then brittle fracture criterion. The material properties really determine which type of mode of failure we're going to have. Okay. So now we're going to switch over and start talking about fatigue a little bit. All right. And we're going to go back and start talking about sort of some observations of fatigue, and then what leads to fatigue. What does it look like? And what happens at the nanoscale and microscale that initiates these cracks. And then we'll get a little bit more quantitative in the next lecture. All right, so and we'll specifically start talking about high cycle fatigue. So high cycle fatigue is not as, you don't have as much intuition about it in your everyday life. You have more intuition about low cycle fatigue, because if you take a staple or a paper clip and you start bending it like this, right, because you're fidgeting, and you basically bend it and it does not bend back into shape, that's low cycle fatigue. So we have a lot of experience with that, where you take a paper clip and you're fiddling with it and you bend it, oh, that's cool, and then you try to bend it back and it breaks, right? So that's low cycle fatigue. High cycle fatigue is more important for mechanical design of components, right? Like large things that carry a lot of weight. And high cycle fatigue is a little bit more important because low cycle fatigue often involves visible strain, right, that you've induced and residual stresses into the part. High cycle fatigue doesn't have those empirical hallmarks, but rather it looks like when high cycle fatigue causes failure, it looks like from sort of an outside observer that something is operating just fine, maybe like a rotating shaft, and then all of a sudden the thing breaks in half, and you're like, what happened? Right? This is not a yielding failure. It just looks like it was operating just fine. It had cyclic stresses, but they weren't past the yield stress, and all of a sudden, ting, the thing breaks, right? So that's why high cycle fatigue is really important. Especially when the combustion engine started to proliferate, then this became a lot more prominent. Some of the first fatigue failures happened on railroad axles in the mid-1800s. And one of the people that was sort of a pioneer in studying this was Albert Voller. All right. So I'm going to write his name down. It's a German name. It's got the umlaut over the O. And so there were sort of everyday fatigue failures, like maybe a train would slow down and stop or something like that in 1800s. And then this started to affect, so I'm going to write down 1800s kind of trains, and potentially before that, like super old days like carriages, horse-drawn carriages. But there were a lot of other problems with those as well. And then in the 1900s, let's say mid-1900s, there were ship components that experienced fatigue failures, such as the Liberty ships. Right. And then starting from like sort of 1980 onward, right, there were various other things that happened with aircrafts and railroads where the trains are now going much faster than they did in the 1800s. Aircraft engine failures, aircraft fuselage failures, and all kinds of things. And so it's an important problem to understand such that you can design against it. Okay. So fatigue failure happens because of crack nucleation, or which is also called crack initiation, and then propagation. Typically, fatigue failures happen around defects, right? Or you could call them imperfections, right? And so this comes into the quality with which parts are manufactured. So let's say you have a rotating shaft, and the rotating shaft had some different radiuses or things turned into it, and the person doing that turning, they flipped off the lathe and they weren't paying attention, so there's kind of a divot by one of those shoulders that they put into it, right? And so in that case, it might sort of meet spec, but there might be a small defect that was left due to machining. And if that defect occurs at a location of very high stress, that defect is now no longer called a defect, but rather that's a micro crack that the plastic strains and these dislocations and slips are going to build up in, and then it's going to turn into an actual crack, then it's going to propagate, right? So machining and the finishes that machining can get can have a lot to do with the fatigue resistance of components. Another type of defect or imperfection can be based in material. Okay? And both of these, both the machining or the manufacturing and materials, are both related to cost of making something, right? So if you want it to be defect-free on the surface, maybe you want it ground after it's machined. To get it really smooth, that's additional time by someone who's trained to do that grinding, right? And then if you want to buy a nicer material such that you don't have defects near the surface where you're getting high stresses, that's also going to cost more money, right? So this is always a balance between what are the resources that we have to build something, and then what kind of potential failures are we willing to design against. So we're going to talk a lot about rotating shafts and fatigue failures. And so what happens is you often get what's called beach marks, okay, on the failure surface. So let's say a rotating shaft experienced a fatigue failure, and now someone's doing like a post-mortem on it, right? They're the forensic engineer, they're coming in saying, okay, what happened with this? Well, what happens is so this is just a rotating shaft of some kind that's broken. And then on one edge of it, whoops, I don't know why it makes like these some kind of glitchy things. Okay, you'll see just like a little curved section like that. And that's where the crack initiated. And then you see what's called beach marks going out from that, because it looks like when waves go up on the sand and then retreat, they sort of leave a little texture where they were, right? And so if that happens, then the beach marks will come out like this. Right? And sometimes they're grouped together, sometimes they're not. Right? And I'm not drawing it super well here, but on the back side. But you can see now that these lines, these beach marks, are where the crack has propagated to, right? And so if there was a defect on the surface here, whether it was dimensional or material based, there's a small crack, and then as more stresses are applied to this component, you've probably analyzed a lot of shafts for the bending stresses. Bending stresses, let's say if this shaft was in operation, there's a bending stress like this, well, that induces the normal stresses at the surface here. And shafts are often driving machinery, so there's torque supplied. So you have, at that location there, quite a bit of stress, right? A combination of normal stresses, shear stresses. And so if a crack starts there, then this shaft, nobody can see the crack initiate, right? It's probably buried inside of a piece of machinery, and then it continues to grow, right? So the crack, if we look at the shaft in a side view, like this, right? It's operating, it's going to get a little crack like that in the side. And then, because of the moments and the torques and all the things on this shaft, this crack is going to want to open up, because the stresses want to pull, the stresses want to pull it apart. Right? And so they're not super high stresses, they're not just going to like yank it apart, but this thing is in operation, rotating with all the stress, so it's going to slowly propagate that crack, and it's going to propagate it in a curved fashion such that it takes up more and more of the area on the inside of this shaft, such that it will reach a point where the remaining area, which I can sort of, if it goes halfway across, then the remaining area, which is sort of this back section here, right? Let's say the contact area, or not the contact area, the area supporting that load is only half of what it was, right? The crack has propagated halfway across, then it can't sustain the loads that are on it anymore, and it will have a catastrophic fracture. These types of cracks have different stages. So stage 1 is kind of initiation of a micro crack. So I'm just going to draw them on here where they might occur in this case. Stage 2 is a macro scale crack that opens and closes, creating those beach marks. And then stage 3, the crack has propagated sufficiently far that it can't support the load anymore, and there's a very quick propagation of the crack. All right. So when we're designing these things, it's very hard to prevent stage 1, right? So we'll just do the best that we can with the finishing tools we have, with the money to buy the high quality material parts. And then what we'll do is we'll design this thing to operate under the fatigue limit, and we'll say with a factor of safety of 2 or 3 or something like that, it'll be fine. Okay? So that's how most of these things are approached. Stage 2, if you can somehow do an inspection on this component, then you can usually detect when things are happening in stage 2. You can see cracks opening and closing, and then intervene and replace the part, fix the part, do something like that in order to get it back. This type of crack opening is called mode 1. If the loading truly does sort of open up the crack and then close it again at the micro scale again and again, anything that opens a crack due to loads just pulling it straight open is called mode 1. There are other modes of fracture as well. And so you can think about what happens if this shaft is loaded sort of unidirectionally, or if it's in reverse bending. So I'm going to draw that on the next slide here. So if we look at a cross section of bending in one direction, it kind of looks like what I drew before, right? It would have its initiation and then the beach marks, right? And then eventually it might have just a rough surface where it fractured at the back. If it has reverse bending, then we know from thinking about this that it's going to have a maximum and minimum stress that totally reverses. So it might have an initiation on one edge, and then shortly after that might have an initiation on the other edge, right? Because the stress is reversing from top to bottom, and then eventually it will break apart, right? Or now you can add in shear stresses, right? So this would be unidirectional bending, reversed bending, or if there's a high torque component, you can have torque plus bending. And that's where you get things growing a little bit in a weird way, right? So if it starts here, then it might actually come out and like propagate around the edges more, right? And then the beach marks might happen in sort of some different geometry, because we know from thinking about shear stresses that the maximum is always at the periphery, right? So if the maximum shear stresses are at the periphery, then the crack will propagate sort of where those maximum stresses are around the periphery before it extends to the center. I told you a little bit about this at the beginning of the semester, like sort of how does this happen at the nanoscale, right? And so what happens, especially at the surface of a material, right, as the cyclic stresses happen, is there may be slip, and then those slip bands might protrude out a little from the surface, right? And I talked about characteristic dimensions of these slip bands and how they might actually go back down into the material here as well and pull the material down in, right? So sort of tens to hundreds of atomic lengths in these slip bands that occur at the top of at a surface. And so now the surface in a continuum sense does not look like a flat line, but it looks like it's got a defect there, right? So if I draw the sort of the surface, what it looks like, right? There's a defect there now. And so that defect acts as a crack nucleation. And then if you have a lot of these slip bands that continue to build up, then you can initiate a crack, and then it's called a macro scale crack, right? And so the words that are used to describe this, we called like slip bands, right? And then when they build up and come out of the surface, then they're called persistent slip bands, because they don't go away or sort of cancel each other out. Right? And then you continue to have cyclic stresses. And these act as little stress concentrations, which then move up from the nanoscale, the microscale, to the macroscale, and they can be seen. What further causes this issue is not just that it's a stress concentration. It's not just that, there was, let's say, a little divot on the surface or something like that, but it's a stress concentration at a location where all of the crystal structures are oriented. So it's not like there's grain refinement and there's different tiny grains, right? If there's a lot of small grains in a ductile metal, then that serves a toughening effect. But these are defects that actually are not like at a grain boundary that has these toughening effects. They're actually on the slip planes that are more likely to maybe slip again. And these cracks can even go through different metallic grains if the slip planes are organized in such a way that they're likely to do that. So this would be like stage 1, kind of at the surface, right? And then several micro cracks join, and the open crack moves. That's stage 2, right? And then we get catastrophic failure at stage 3. Okay. So when we talk about fatigue, you've probably drawn many of these SN-type diagrams in your prior classes. But if you don't remember them, we have stress on the y-axis. And this is the stress amplitude, let's say, of a cyclic stress. Okay. So we could have some location in our part, right, that's experiencing a stress like this. In this case, that would be fully reversed. It would go positive to negative with equal magnitudes. And so that it has a stress amplitude A, right? And so that stress amplitude, if we plot that, this would be like in time. But if we plot this according to cycles, then lots and lots of experiments show that there's a high region and it decreases like this. And there's a lot of uncertainty in this, right? It's not a perfect line. And then eventually it sort of plateaus off, right? Something like that. And we call this flat region the endurance limit. Right? And if you have stresses that go below that, you don't really have to care about fatigue because you are expecting the material to have very long endurance. Okay? So that's the endurance limit. And let's say that you choose a particular stress amplitude. Let's choose like something right here. Okay? So let's say we start an experiment at that stress amplitude. Okay? So let's say we have just like a bar, and the bar is rotating at a constant speed, and then a side load is applied. So if we have a side load on a rotating bar, at any location on the surface of the bar, it's going to experience cyclic stresses that are tensile and compressive alternatingly. So that's kind of what I drew like on the top right here. So that's stress amplitude. So let's say we start running that experiment, and every time it goes through that cycle, that's one cycle on this x-axis. So every rotation of the bar is one cycle. Okay. So we start the experiment, and we start coming over here, and we just measure when the bar just fully fractures. Okay, so we run it for X amount of cycles, and we come over here, and oh, okay, it fractured. We take note of the cycles. Maybe it's like, I don't know, 10 to the 4 or something like that. So maybe it's 10,000 cycles. And so that would be a data point of final fracture, right? But we talked about the stages, right? Stage 1, stage 2, stage 3. There must be something happening before we get to that. So we could draw sort of a line here, and I'm just going to sweep with broad stylus strokes here, right? So we can draw sort of a curve here, and then we can come down, we can draw sort of another curve here. And so when we would expect that the stages would progress as we go, whoops, come back. Okay, stages would progress as we go according to our experiment this way, right? The more cycles we apply. And so the first thing, what's going to happen is the crack initiation. And that will happen at some number of cycles that we can't really tell. We don't really know, right? Something like that. And then if we keep stressing it, keep running it, eventually it's going to reach that fracture. And so this width here in kind of the spread of the data can show us when all those final fractures occurred, but we know there must be a window at which the crack was propagating before we even got to that. Okay? So this window that I've drawn on here is like the crack growth region. Okay. So you can start to incorporate, I guess, sort of these atomic scale understandings into what you already know about fatigue, right? And this was one of the earliest discoveries by that researcher Voller. Okay. So these types of SN plots are all for high cycle fatigue. And we say that high cycle fatigue is greater than about 10 to the 4th cycles. On your SN plots, you may go back to kind of 10 to the 3rd, just for like a reference point. But if something fails at less than 1,000 cycles, or maybe even up to 10,000 cycles, that's low cycle fatigue. If it fails at sort of greater than 10 to the 4, and then up to 10 to the 6 in some cases, or 10 to the 9th in other cases, depending on the conventions that you're thinking about, those numbers of cycles, so 1 million or 1 billion, those are considered infinite life. The stresses are low enough where we don't expect any cracks to initiate. So that's kind of the general approach to thinking about fatigue. And then the way that many of the things, phenomena we need to consider were discovered was just by a lot of testing. So what I talked about, having a rotating bar with a side load, that's a very standard fully reversing fatigue test. And so there were researchers that had sort of a bar that was nicely finished and smooth across the whole thing. Then there was a bar with a notch in it, and there was a bar with a groove in it. And they would map out what does this stress to cycles curve look like for all of those different conditions. And that's how they came up with the ideas that stress concentrations matter in cyclic loading a lot more than they do in sort of quasi-static loading. And so we are going to talk about both high cycle and low cycle fatigue in the class. So high cycle fatigue is going to focus on kind of that crack opening, right? It's that sort of pseudo-stable zone where cracks are propagating. And we're going to think about this with linear elastic fracture mechanics. So we'll have to do an introduction to fracture mechanics and then talk about how fatigue applies to that. And high cycle fatigue predicts crack growth. So crack length is typically denoted with a lowercase a, so I'm just going to use that. So it predicts crack growth the length of A there, by stress intensity. All right. So that's why I said things about like, stress concentration factors and how long the crack is and how sharp is the crack tip. All of these things come into what is the stress intensity at the tip of that crack, that every time you go through another cycle, the crack's going to open up just a little bit more. Okay. Okay. Hang on a second. Let me make sure I get this right. Okay. Then, from high cycle fatigue and thinking about linear elastic fracture mechanics, what we're going to do is the method we'll use to analyze this when the crack is growing, so crack growth, and it's called the stress life method. So that's the introduction of this is what we've already had, thinking about those SN plots, right? S was stress, N was cycles, or we can convert that to a lifetime. And then we'll also talk about strain life, which is a little bit more complicated and is for low cycle fatigue. And the reason it's more complicated is it focuses on plastic deformation and crack nucleation. So anytime we have to deviate from linear elasticity and go into plastic deformation, it gets a little bit more complicated. So these are the things, these are sort of the key words and the things that we're going to do when we talk about these kinds of methods. Chapter 7 in the book is the stress life method, and it's a good starting point. For low cycle fatigue, or for situations where you really want to design in exactly how many cycles something would need to fail, you have to consider the plastic deformation and the strain life method. And so that is occupies a couple of chapters in the book. There's linear elastic fracture mechanics, which is chapter 3, and then also extending into chapter 8 and 12. And then at the end of this, we will talk about fatigue design criteria. So we talked about design criteria as failure criteria, as avoiding a yield stress. You can also have fatigue-based design criteria. That should be done in addition to static considerations. And so when you think about your other classes, you might be taking classes in finite element methods and things like that. So those are good for complicated parts that you can't estimate the stress states very easily analytically. But they often don't extend very well into cyclic loading, plastic deformation, and things like that. And so this is where an understanding of fatigue can really come in handy, such that you don't use simulation software where you're predicting something that is only based on linear elasticity or static loading when the real situation doesn't have that. Okay. For these fatigue-based design criteria, I already mentioned one where you might say, I'm just going to stay below the endurance limit, and I'm just going to design for infinite life. All right. If you don't have the ability to do that because your parts have to be too big, or they have such high loads that it's unlikely to work, right? Then you can talk about something called a safe life design, where you say this thing is guaranteed up to 1 million cycles, right? So this would be safe life design. I would say applies to something like bearings. So in some of your other classes, you might have had like a bearing selection module of some kind. And what they do is they provide statistics, right? So this bearing will work up to X amount of life under these kind of loading conditions. And so that would be like a safe life design. So then you put into your machine operation, replace bearings after X amount of hours. This can be also incorporated into a fail-safe design, where if you don't know, if you have a lot of uncertainty in planning for fatigue, then you put in place things that are going to prevent overall system failure. Okay, so inspection schedules, right, that are pretty heavily used. Progressive failure, where you design one part, and then if that fails, it sort of rests on another part that can sort of take over for a little while. But you see, oh, that part stopped working. Let me go in and do that. And so these kinds of designs are often used in applications with high consequences for failure, like aircraft and things like that. Especially, you would think that something that's been around as long as trains have, that they would be able to move past this. But there's a lot of work, even research going on into non-destructive damage detection on railway rails, such that they don't have to keep sending out technicians to inspect them so frequently. And then you can also have damage tolerant design. So I have no more space to write, but damage tolerant design, where you're not trying to prevent fatigue, but you assume that there's going to be a crack eventually. So how can we design this to resist further crack growth, right? So you sort of try to predict the progression of how things are going to operate. Okay. So I just wanted to give you sort of an overview of what's to come. We'll start talking about the stress life method and these kind of SN curves, and go from there. So I'm going to end the lecture there for today. There is a problem set due on Monday at 8 p.m. So if you have questions about that, my best advice is to post it on the class discussion board. There are already 5 posts, I think, on there, and so it's a good resource because I think all the questions are helpful. I've tried to answer as many as I can. You all are welcome to jump in and answer them with your advice as well. I would just ask that you don't post any solutions on there. So if I don't see you at some point before then, I'll see you in class on Tuesday, the next lecture. I have established an extra office hour this evening by request. So if you want to jump on Zoom around 7 p.m., I will be there. I put it on the course calendar and also made an announcement about it on Canvas. It would be a really good time to check how you're doing on the problem set if you're struggling, or if you don't know where to begin. It's a good time to begin. But I also have office hours on Friday at lunchtime-ish and Monday at lunchtime-ish. So you can make use of that as well. All right. Thanks.